Hi everyone, I'm Sylvain. Back in 2007, I was finishing my PhD in Paris in the Tao INRIA team in the University of Paris South. And now I'm part of the Google Brain team in Zurich, Switzerland.
And I'm David. Back in 2007, I was doing my PhD at the University of Alberta, and now in 2017, I'm at DeepMind. I'm really sorry we can't be there in person, but we prepared this presentation, and I hope that makes up for it.
We are going to take you in a journey, and a very specific type of journey, a time travel. So we're going from 2017 to 2007, and then there we are going to show you how techniques from reinforcement learning and Monte Carlo research could be used and combined to improve the computer Go state of the art. And then we are going to show you how over the year those techniques have evolved up to Alphago with, in addition, the use of deep learning. Even though we are going to focus on computer Go as it was the main application, other improvements have led to applications on games, but also beyond games. And now, close your eyes and imagine you are in 2007. Of course, in addition to all being 10 years younger, there have been significant differences. One is that deep learning was not yet rebranded, was not reinvented. Of course, people were using neural networks at that time, but it was much less mainstream and much less used and also less powerful. Also, reinforcement learning, even though there have been a lot of past success, was not so taken seriously and not so used in many places and was not considered as something you could just take and use for your applications. And in the specific case of computer Go, the level of traditional programs at that time was just barely at the beginner level and using techniques like alpha beta search, which was the state of the art.
So if we think about artificial intelligence as a whole, there's one fundamental problem which is at the heart of it. And that's the question of how do you get an agent to achieve a goal? And planning really focuses on this problem. It says that if you're given the rules, if you're given a model of the dynamics or of the transitions in your problem, how do you pick a sequence of actions so as to achieve that goal? And so really, this is the fundamental question of AI. And computer Go became a Drosophila for this particular planning problem. In other words, it's the testbed that many people focused on, and many people viewed it as a grand challenge for planning. And the litmus test to show that if we really made progress in this domain, that we really would have made some significant strides towards many other kinds of planning problems. And so Go in particular is nice because it has very simple rules. In other words, this model that we know is very straightforward, and it can be simulated very efficiently and effectively. And also we have a nice way to test our performance by simply playing games against humans and seeing how well our programs actually perform in practice. So if we compare Go to something like checkers or chess, domains where traditional search had been very effective, we see that there was a big difference. That for those domains, there was a more limited branching factor and a more limited depth, leading to a more manageable search tree. So if we think about the game of chess, for example, there's a branching factor of around 40 in each position. There are about 40 different legal moves that can be taken. And the game lasts for around 80 different steps over the course of the game. And in particular, it's also possible to make quite a simple, straightforward evaluation of a position by simply adding up the piece values for black and white, and that already gives you a very simple indication of who's actually winning in that position. If we contrast that to the game of Go, we see that in Go there's something more like a few hundred possible actions in each position, and the game lasts for several hundred different steps throughout the game. And as a result, the branching factor becomes absolutely enormous. And on top of that, there's this fundamental problem of how to evaluate a position. So in the game of Go, each position has some scattering of black and white stones, and you have to predict from that position, where we typically have the same number of black stones as white stones, who is going to win in the game. And this became a large and unsolved problem, which led to many of the techniques we'll talk about today, including Monte Carlo search and deep learning approaches. So if we look at progress in computer Go before 2007, we see that these traditional search approaches based on algorithms like alpha beta search had somehow stalled. They'd reached this kind of beginner level, which is known as amateur Q level in the game of Go. And then it somehow stalled at roughly this beginner level and was not able to really scale up in this very large and challenging search space.
So now, how do you find a good action for a given position? So one approach, one dimension of the approach is to take decision online, which means that given a position, given a state, you are going to spend your compute resources at that state to compute the best action for that particular state. And that's the advantage, that you don't need to solve the whole problem. You just need to focus and find a good action for this particular position. And so that means it's a local search. And we are going to focus ourselves to a particular way to do that. Using, when you have a model, you can do planning or search. And of course, you can use alpha beta with evaluation function like in chess or like in the traditional computer Go programs. But here we are focusing on sampled planning. So the simplest way to do samples planning, how would you do it, is let's say you start with a position here and you want to compute its online value, V of S. And what you can do is, given a rollout policy, and we're going to see later how you could build that, but assume you have some rollout policy, you could use this policy to play against itself up to the end of the game several times. And once you are at the end of the game, what you can do is just count which side is winning. So now you get the outcome from there. And with Monte Carlo, the simple thing you'd say is that the online value you get is simply the average of the outcomes divided by how many times you tried. And as you do more simulations, you will reduce the variance of this estimate and it converge to the expected value of the rollout policy playing against itself. But you have to remember here that the rollout policy in this case is fixed, which means that even with infinite compute power, you're not going to converge to the minimax value. So now how could you improve that beyond that? And that's the idea that came on Monte Carlo tree search. The idea is to say, if I'm going to spend more compute time, shouldn't I just improve the policy iteratively? And one way to improve the policy is to build a search tree and remember the online value so that you can use it to improve. And now the policy will have two parts, one which is inside the tree, and this one will improve over time, and the other which is the same rollout policy as we've seen in Monte Carlo. So just deep diving into a concrete example. So let's say you have this position. You can, at the first iteration, you're going to just use, like in Monte Carlo, the rollout policy up to the end and get the outcome and just keep it, which means like the value at this node is 1/1. But now, contrary to Monte Carlo, when you do the second trial, you're going to expand your tree and remember not only one value at the root node, but now two online values that is going to keep the outcome, the average outcome of the nodes below that. So here, when you expand this tree, let's say you try the right-hand side move, you're going to use your rollout policy up to the end, and in that case, you get a 0. So this node gets an online value of 0/1. But this node, the roots, keep the value of the previous one, and so now you have 1/2. And you keep extending that, let's say twice, and now you have like these 4 nodes in your tree, and at each node you keep different value, which corresponds to the average outcome of the nodes below that. And now the question is, what do you do with this value and how do you expand? So one idea is UCT, which stands for upper confidence bound for tree, where you are going to see how you explore, how you change your policy to explore the tree. So let's take the simplest idea. Let's say you have this tree. For each node, you have the online value you computed so far. And one idea is to say, if I want to choose which action to explore next, I'm just going to take the one that has the highest current value, so the highest average, which will be this path. And you're going to try from this node to see what's next. And that will be using the best online value. But you can see that if you were to choose the right-hand side node, so far you did 0 reward out of 2 trials. But what if you were just unlucky, that these were actually wins, but you got unlucky because there is randomness after? Or what if this side was lucky? So you need, in addition, another term, and that's what this term will play. So just to explain a little bit the notations, here we talk about the value for state and an action. And these terms, the n of SA is saying how many times did you try the action A in state S? And NS is simply the sum of NSA for all actions, which is the number of times you visited this state. And you can see that these terms, if you did not try a given action in a state very often, this term will be big. So we will be encouraged to try this action more likely. And this term will will go to infinity, which means that you will always try visit all state infinitely many times. And the nice thing with this algorithm is that under some condition, it converges to the minimax problem at the limit of compute. But now something to be said is that here you assume that at the limit you can observe all state and all action infinitely many times, which of course in practice is completely impossible. So even though with this exploration term you can explore everything, you can't really do that in practice. So you have to have other techniques, and we are going to show that later. And actually with the techniques we are going to show, just an anecdote is that at some point the Mogo program was having a C constant of 0, which actually removes this term. But OK, so now that you have this algorithm, one question is, how do you, what are the limits? So one limit is that because you build a search tree, and in the search tree you keep the value as a tabular function, you don't have no generalization, which means that what you compute on a given position will have no effect on what you compute on another position. So you don't generalize. And the other thing, which means that if you did not observe this position in your tree yet, then you have no knowledge. And finally, for each Monte Carlo evaluation, you just get whether you win or lose, which is a very high variance estimate, as we've seen. So you need many explorations before you get any precise estimate. So one idea we introduced is to have this rapid action value estimate. And what is the idea? Is to say, let's say you have this search tree, and here are the simulation out of the tree, and you want to compute the online value of C3. And you see that from this node, you play C3 only once, and you add an outcome of 0. So the value, as we explained before, is 0/1. But you also try other move here, and you did play C3 later in the game, so you have some information. And the simple idea here is to say, maybe I can look at the other games where I play C3 and then have a faster estimate of how good C3 is. So if a game where I play C3 is a win, maybe C3 has some value. If a game playing C3 is a loss, maybe it's not so good. And so in that particular case, you see that you play C3 actually 5 times, and you won 3 times. So the rave value of C3 is 3/5. And again, you can do that on all nodes. And so for this node, you play C3 3 times and only once as the next move. So the Monte Carlo value of this move is 1/1. And the rave value of C3 is 2/3.
So I'm now going to talk about a very different kind of knowledge which we used back in 2007, which is the second idea, the idea of offline knowledge. And so this is another type of knowledge, and typically we can think of these as like predictions that are estimated offline. We're going to talk about 2 particular kinds of prediction, the value function and the policy. And what's different about these is that these are now global to all states. Because we're learning offline, we don't actually know which states you'll encounter when you actually play the game online. And so we need to approximate every possible state that you might encounter, which in the game of Go might be 10 to the 170 states. We're going to come up with some kind of estimate of this entire space. And ideally, we would like to estimate these quantities by reinforcement learning methods, although it's also possible to use other techniques such as supervised learning or even handcrafting. So we can think of this as the more familiar technique nowadays with machine learning. But it's really, we should note that this is in direct contrast to the kind of knowledge that Sylvain was just talking about that's computed online within the search tree. So back then in 2007, we didn't have such knowledge of convolutional networks and so forth. They were around, but they hadn't been proven to be quite so effective. So we tried something more naive, which was to look at these, what we called shape features, which were 3x3 patterns, which basically indicated whether a particular pattern was matched in some location of the board. So for example, did this particular pattern of black and white stones occur here? If it did, this particular feature would have a value of 1, and if it did not occur, it would have a value of 0. And this gave us a very large binary feature vector containing about 1 million different elements. And we estimate the value by taking a linear combination of all of the patterns which are present in this position with some weights. And that gives us our estimate of who is going to win in this position, whether it's going to be black winning or white winning, just based on these particular patterns that are occurring. And these weights can be trained by self-play reinforcement learning. And so what we tried was using temporal difference learning, so the TD lambda algorithm, to train the weights of this function approximator and figure out an effective value function to estimate who was going to win from each of these positions. And we also had some handcrafted knowledge to compare to. And so once we actually have this knowledge, we can insert it into the search tree. So we can combine this offline value function that we figured out by offline reinforcement learning with the kind of knowledge that Sylvain was just talking about, this online values that were computed from the Monte Carlo simulations. And so in particular, the way that we do that, that we tried back in 2007, was we tried to initialize the node with the value which was computed offline. So instead of just starting when you create this new node, so imagine this is a node that's visited for the first time. So previously, we would have just initialized that node to say, well, we haven't visited this any time, so it's got a visit count of 0. And we've got no idea what the value is yet, so perhaps we assign it a value of 0. And instead of that, what we do is we now initialize those values using our offline value function as our estimate of who's going to win, and using some estimate of how much we trust that offline value, which we use to initialize the count. And so we can think of this as some kind of prior knowledge. So in particular, it takes the form of a beta prior. And actually, when we initialize, this is a bit like saying if our value function was 0.3 and we've got a count of 10, that's like saying it's just as if I'd seen 3 wins out of 10. I'm going to trust this offline value as much as I would have trusted seeing 10 online simulations and computing a value online from those 10 simulations. And this idea was very effective and became one of the core ideas that was used in MoGo and subsequent programs. Another idea that we tried was actually training a different form of offline knowledge. This was the offline policy. So instead of training a value function offline, we train a policy. So actually what we tried was using exactly the same representation and just taking the value function which we'd learned and basically using a softmax over that value function to come up with a policy. So in particular, what we did was we said, OK, for each of the moves which you could play in this situation, let's imagine the patterns which would be activated if you were to play that move, and then make a softmax over all of the values that you would reach. And so we now have actually what was quite a stronger policy trained in this way, much stronger than handcrafted policies that were available before. And we can ask, how well does this policy do when we use it? So how can we use this policy? Well, the most obvious idea, perhaps, is to insert this policy into the search process and use it as a rollout policy. In other words, whenever we run this Monte Carlo tree search, we're running one simulation, and whenever we reach this kind of rollout phase of the algorithm, we run our rollout, and instead of picking actions the way we were before, we're going to use our learned policy to insert this offline policy here to pick the actions all the way to the end of the game. And you might think that by using a much stronger policy there, that we would end up with more effective estimates of value in the search tree. One of the big surprises of this paper that we had in 2007 was actually this turned out not to be the case. And I think this was a surprise to many of us at this time. So surprisingly, having a much, much stronger offline policy did not lead to a more effective rollout policy. So in particular, we had this learned policy which had been trained by reinforcement learning, and it was winning almost all of the time against a handcrafted policy. And yet when we plugged it into the search and we looked at the Monte Carlo values which were being estimated in the search tree, the Monte Carlo values were actually much less accurate. And we believe that this is because of the diversity was being lost. So when you actually use reinforcement learning, it tends to find the greediest and best action, and there's no incentive for it to maintain diversity. And so actually, in future work, in subsequent work, people tended to more use supervised learning, which maintains diversity simply because humans tend to have a more diverse selection of moves. And so that representation maintains diversity. We also had some subsequent work with reinforcement learning where we showed that additional techniques were able to address this paradox by actually balancing the diversity more directly.
And those techniques that we described between the online knowledge part and the offline knowledge part was kind of summarized in MoGo, which was a program basically built out of those elements. So Monte Carlo tree search plus the rave plus some simple value functions to initialize a node in the tree and some rollout with a custom policy. And this simple combination at the time was giving a big boost in performance And especially compared to the previous kind of generation of programs which were not using Monte Carlo tree search and more alpha beta search, there were a huge improvement. And another thing is that it's also the first program that won a game against a professional. So of course it was 9x9 Go, which is kind of 1/4 of the board, and it was one game out of several, but it was something that was not thought a few years before. And so now if we go back to the timeline, right, where we were showing the traditional search programs and their performance, now what happens with the Monte Carlo search program? So those were Monte Carlo search, not with the tree part, and from there it was with the tree part. And you see that relatively early those lines curve, and the other interesting thing is that the slope of the curve is actually better and show no asymptote yet. And now the question in 2007 was, what is this line? Is it going to plateau very fast and not reach master level at even amateur level? Or is it going to go like a straight line? Or is it going to even explode as more programs are going to use those techniques? And just as an anecdote, when we were like beginning in this Monte Carlo tree search changes with all those improvements, there were a lot of skepticism from more traditional approaches. So actually, Monte Carlo tree search started in smaller boards and started to win against some program, but always it was, yes, but it's not going to beat strong humans. And then when it started to beat strong humans, yes, but that's not the real game. And then when it started to be the real game, yes, but it's not going to beat strong players. And that's what at this time. Yes, it's already beating traditional program, but is it going to beat? And now you have to guess. And we were guessing at this time. And actually we sit down with David and we wrote some prediction or some bets. I mean, it was not really bets as we are mostly agreeing, but we wrote that in the beginning of 2007. We have proof of that if you want. And then we were trying to see, okay, let's see now in the future. And because it's a test of time, I think it's interesting to show how much those test of time. So the first bet was kind of very short term. Within 6 months, one program will beat a professional in the smaller board, 9x9. The second one was within 2 years, a program will reach what's called master level at amateur, like 1 dan in Go. And finally, the big bet, long-term bet at that time, 10 years, one program will be undisputed world champion within 10 years. So I'm not going to spoil, but that was the thing, and we'll see how it went. And after this 2007 kind of era, there have been a lot of improvements, of course, and most of the improvements were on the offline policy, and especially using better features like better patterns, better handcrafted features, and also using supervised, so like human data to learn in a supervised way the policy. And with our stronger policy, another thing that changed is how the offline policy was used online. So as a rollout policy, that's the same as we've discussed, but as the offline policy was also used to bias the search tree. So in the previous thing, we were saying that we use the offline value to initialize the nodes in Monte Carlo tree search. But here the idea is, instead of doing that, when you have to choose which branch to explore, you can as well use your offline policy to bias the search and concentrate to the good moves. And now we extend the line, because that's the nice thing being in the future is that the back prediction are easier to do. So 2007 is here, we were here, and then the question was, is it going up or staying? And interestingly, it went up almost as a straight line, and more and more programs were using those techniques and improving, and up to basically 2011-12, where it suddenly plateaued. And here, note that we are already at master level. It's still amateur level, but it's still already a strong program. So at that time, with more compute and all those improvements, there were a lot of hopes that actually this is going to cross professional. But then suddenly, it's plateaued.
So to bring us up to the present day, I'm now going to talk about the final piece of the puzzle, which was introducing deep learning into the mix. So in particular, when we started on the Alphago project, we introduced a new form of offline knowledge, which was based on using deep learning, and in particular, convolutional neural networks. So the idea was to have a much more sophisticated representation of knowledge of the game of Go. And so the way that that worked was that in each of these convnets, we would take in a 19 by 19 input describing the black and white stones in the position, and that would get fed through many, many layers, giving rise to increasingly sophisticated features which were representing the board at a higher and higher level. And ultimately, this representation could be used as knowledge, as this offline knowledge in various of the ways that we've already seen, and some new ways that I'll now describe. So there were actually two types of offline knowledge in Alphago, a value network and a policy network. So the value network was actually a deep neural network which took as input this position, passed it through many layers, 12 layers in the original Alphago and many more in more recent versions, and finally output a single scalar value. And that value basically indicated whether we thought that the current player would win in this position. Do we think that black is going to win, or do we think that white is going to win? The second form of knowledge that we used in Alphago is the policy network. So the idea of the policy network is, again, to take a position as an input to the neural network, pass it through all these different layers, but this time to actually output a probability map. And that probability map is basically saying how much preference Alphago has for selecting a particular move in this whole board. So in this particular example, it really likes to play this move, also likes to play some of these other moves, and it really isn't very keen on some of those other moves. And so these are the two forms of offline knowledge that we used in Alphago. But how were they trained? Well, we actually used a machine learning pipeline that consisted of both supervised learning and reinforcement learning. And the whole of these training pipeline was, when we introduced Alphago, was completely offline. So if we start off with these human expert positions, we start off with an expert data set that basically says, what would a really strong human player play in this position? And then we apply standard supervised learning techniques to basically train the policy network to predict the move which was played by the human expert in each of those positions. And that gives rise to a very nice representation of policy that's able to predict much better than previous approaches what a human would do in each of these positions. But then we want to go further and apply reinforcement learning to this. So what we actually did was we took the policy network and we got it to play against itself thousands of games of self-play, and we applied reinforcement learning both to improve the policy network by policy gradient techniques, but also to estimate now the value network. So specifically, the value network is trained so that basically what we want to do is from each position, we play a game of self-play of the policy network against itself, and we ask the value network to predict who would win from that game of self-play. Do we think that black will win from this position, or do we think that white will win from this position? And this gives rise to a very nice estimate of value. In fact, this was the first time in the history of Computer Go that we had a reasonable estimator, a kind of strong estimate of really just from this scattering of black and white stones, who is going to win in this position. So now we've got those two forms of offline knowledge, how did we combine them with search? How did we combine them with the online knowledge that we have in a Monte Carlo tree search? So we actually used two ideas. The first idea was to use the value network to actually replace the subsequent search tree, which we would have previously had to do at each node of a search tree, at the least leaf nodes. So you can think of this as much taking the place of an evaluation function in a traditional game tree search, like the evaluation function in a chess program. Now we have something where we reach this leaf node here, and we simply query AlphaGo to say, who do you think will win? Do you think black will win, or do you think white will win? And instead of having to do subsequent search, we can plug in that offline value and combine that with the online values which are being computed in the search. And so you can think of this in some way as, if we compare it to what was done before with Monte Carlo tree search methods, previously we could think of it as the values that were being estimated as a bit like crowdsourcing. It was a bit like asking like 100 weak players to play games against each other, these rollouts, play games against each other, and then ask these 100 players by crowdsourcing to estimate who was going to win. And if 70 out of the 100 players actually won in their games of self-play, then we say, oh, well, the crowdsourced value estimate would be 0.7. In contrast, the new idea in AlphaGo is to replace those hundreds of weak players in crowdsourcing with one strong estimate. And so the intuition was that if you ask one strong player who is going to win from this position here, that estimate of that strong player will actually be more valuable than the crowdsourced estimate of many weak players. And indeed, we did find that to be the case. So we can think of this as the offline value really replacing the role of rollouts, or augmenting the role that we had with rollouts, and replacing those online values with something that was trained offline. The second idea in Alphago was actually to reduce the breadth of this enormous search tree. And so the way we do that was actually to bias the search tree towards the most promising branches. So here, we basically use this powerful policy network to recommend paths through the search tree. So from each position, we use this offline knowledge to say, actually, it's going to be more likely to lead to a good outcome if you go this way rather than this way. And those recommendations basically ensure that the search tree focuses on the best regions of this enormous search space. So basically, Alphago combines these two methods together, reducing the depth with the value network and reducing the breadth with the policy network to actually address the enormous search space that we have in something like the game of Go. So when we put it all together in Alphago, we actually achieved some nice results. So starting in 2015, we were able to defeat the European champion Fan Hui by 5-0. The next year, we actually defeated the 18-time world champion Lee Sedol by 4-1 in Seoul. And finally, this year, we were able to defeat the world-ranked #1 player Kujie by 3-0. So if we go back to our timeline showing how progress was made with traditional search, and then this takeoff that Sylvain was explaining with Monte Carlo search, which eventually asymptoted, we see that actually deep learning kind of took up the slack and was able to come in to the rescue. Just when we thought that our bet was looking difficult, this deep learning really led to a spectacular acceleration of performance, taking us beyond these amateur master levels into the professional regime and ultimately beyond human capabilities. So just to summarize, so far in this talk, we've presented several different ways to combine online and offline knowledge together. And we've seen that throughout this timeline from 2007 to 2017, there have been several different ways in which these different types of knowledge have been combined together. So starting in 2007, back with the original paper, what we saw was that in the program Mogo, we actually combined together offline values and online values in each node of the search tree. So specifically, each node of the search tree was actually storing a value, and that value combined together Monte Carlo estimates that were computed online from rollouts, Rave estimates that were computed online by generalizing across actions within those rollouts, and the offline value function, which was either estimated through reinforcement learning or handcrafted. And these were combined together at every node of the search tree to give a much more effective estimate of value, which led to much stronger progress than previous approaches to Monte Carlo tree search. In addition, Mogo also used an offline policy, either trained by RL or handcrafted, to actually give a more effective rollout at the end, at this rollout stage of the tree search. If we then move on to the intermediate stage, programs like Crazy Stone and Zen and many other programs in the intervening period augmented those ideas and also introduced many other ideas we haven't had time to explain. And what they did was, instead of focusing so much on value, they started focusing more on policy. They learned an offline policy by supervised learning using handcrafted features. And that offline policy was used, instead of directly affecting the values in each node of the tree, those offline policies were used to influence the decisions that were made from each node of the search tree. So this was basically used to skew the UCT-like selection rule towards actions that the policy believed were most likely to be successful. And in addition, the offline policy, a simpler version, a faster version of the offline policy, was also used during the rollout phase. Finally, if we move on to Alphago, we see a kind of return to something which was more akin to traditional search. The idea of using an offline value function now to actually something more like an evaluation function itself. So the idea was that we trained this very powerful offline value using a convolutional neural network. But instead of just affecting that node in the search tree, the idea is this is treated like an outcome that's actually backed up through the entire path of the tree that actually led to that position. So instead of just influencing that one node, it influences the entire structure of the search tree. And this turned out to be a more powerful idea that led to more effective results in practice. In addition, the online value, which this is combined with, was based on Monte Carlo outcomes, like averaging over these values. but that we no longer found it helpful to use the rave idea. And finally, we used an offline policy, again, to influence the action selection that was taken, using, again, a skewing of these UCT-like equation to actually prefer to pick actions which the policy believed were most successful. So there were two things which changed. First of all, the nature of the offline knowledge was much more powerful due to deep learning. But in addition, there was also this more effective way to combine online and offline knowledge together.
And now back to our prediction. So now that you've seen everything, you should be able to score 3 out of 3 after this exam. So the first prediction was, can we defeat a professional in 9x9 in the short term? And as we discussed, Mogo actually in June 2007 was winning 1 game in an exhibition match. Then the second thing is, can we achieve master level at amateur level within 2 years? And actually it happened in 2 ways. So first in a weak way, where Mogo won 1 tournament at this level, and in a more consistent way by then in 2009, which still fits the 2 years time frame, and was reaching 1 dan consistently. And then finally, you all know about the world champion, and as we say in French, you're never better served than by yourself, and David had to go to the rescue to our prediction.
So just to finish, I really wanted to say thank you to the organizers of ICML for this nice award, and very unexpected, but we really appreciate it.
And thank you again, and I'm happy to take questions now.